Okay, here's Edexcel 2017 paper 2, starting off with multiple choice. Number 1, which of the following wave properties is not exhibited by sound waves? Diffraction, technically yes. Interference, yes. Polarisation, no, because it's a longitudinal wave. 2, two identical springs are arranged side by side as shown. When a force of 20 newtons is applied, an extension of 8 centimeters is obtained. Force of 5 newtons is applied to one of the strings on its own. Which of the following is the extension obtained? So we know that F equals Kx, but when we have two springs in parallel, the spring constant is double the equivalent spring constant. So F equals 2Kx. So we could look for K and then just bung that into F equals Kx for the second situation, or we can just say F1 equals 2Kx1. But then in the second situation, it's just one of those springs, so it's F2 equals Kx2. So we can say that 2x1 over F1 equals x2 over F2. So that gives us 16 divided by 20 is equal to x2 divided by 5. That gives us 4/5. So therefore x is equal to 4 centimeters. It's B. Question 3. A playground swing completes 21 oscillations in 1 minute. Which of the following is the frequency of the oscillations? Time period is going to be 60 seconds divided by the 24 oscillations. Frequency is the reciprocal of that, so we can just flip it on its head. 24 over 60, that gives us 0.4. It's B. Question 4. Which of the following is not a similarity between gravitational fields and electric fields? For a point charge or point mass, follow if yes, that is the same for both. Oops. For a point charge or mass, the field is radial. Again, it's the same. Both fields act at a distance. That's also correct. Both fields act on all particles. True for gravity, not true for electric fields. The correct answer is D. 5. A data book contains the following information for ethanol: latent heat of fusion, latent heat of vaporization. 545 joules is transferred from a sample of ethanol when it condenses. Which of the following shows how to calculate the mass of ethanol that condenses? Well, we know that energy is mass times latent heat. So if you want to find out the mass, it's going to be the energy divided by the latent heat. We have fusion, that's melting and freezing, and vaporization, that's condensing and vaporizing. So it's this one that we're talking about. So therefore it's going to be 545 joules divided by this. It's B. 6. 4 regions A, B, C, D are labeled on the Hertzsprung-Russell diagram. Which region includes the position of the sun? So A, B, C, D. It's going to be B. This is the main sequence star region. 7. Black body radiator of temperature T and surface area A has a luminosity L. Which of the following is the luminosity of a black body radiator with surface area A over 2 and temperature 2T? So the Stefan-Boltzmann law is L equals sigma AT to the 4. So we can say that L is proportional to AT to the 4. What's happening to A? That's going down by 2. What's happening to T is going up by 2 to the 4. So ultimately the whole thing is going up by times 2 to the 3. It's the same as times 8, so the answer is D. Line in the hydrogen spectrum of a star in the Milky Way is observed to have a wavelength of 656.3 nanometers. In the laboratory, this line was a wavelength of 654.9 nanometers. Which of the following expressions give the magnitude of the velocity of the star relative to Earth? So we know from Doppler effect that the change in wavelength by the wavelength is equal to V over C. So if we want to find V, that means that we have to stick C on top, so we times by C here. So the only one with a change in wavelength is D. An object is placed 6.5 centimeters away from a lens of focal length 3.9 centimeters. An image is formed 9.8 centimeters from the lens. Which of the following is the magnification? So they're trying to catch us out here by actually giving us the focal length. You don't need that to have the magnification. Magnification is image height divided by object height, but it's also equal to image distance divided by object distance. So 9.8 divided by 6.5. That just gives us 1.5. So they've tried to catch us out. Very sneaky. 10. A beam of light from a laser is directed at a diffraction grating. Diagram shows the position of the central maximum, first order maximum, and first order maximum either side. Which of the following could cause the first order maxima to be closer to the central maximum on the screen? So we want that to be closer. So we want theta to be smaller. Moving the laser closer to the grating, no, that's not going to affect anything. B, moving the screen further from the grating, no, that's going to result in wider fringes, wider orders. C, using a grating with more lines per meter. Well, if we have more lines per meter, that means that D goes down, so that's also wrong. Using laser light with a higher frequency, if we have laser light with a higher frequency, F goes up, but that means wavelength goes down. And you should remember that if you have higher wavelength, you get more diffraction. So if you've got a smaller wavelength, you get less diffraction. It is D. Question 11. An electric iron rated at 2600 watts contains a steel plate which is heated to a working temperature of 215 degrees C. Room temperature is 18 degrees C. Deduce whether the plate could reach its working temperature in less than 1 minute. Okay, so we need to first of all find out how much energy goes in. So that's E equals mc delta T, or mc theta. So that's going to be 0.89 times 450 times our temperature change, 215, take away 18, that gives us 197. So what is that? 78,900 joules. And then we've been given the power, but we want to find out the time. So power equals energy over time, or work done over time. So that means time is energy over power. So let's do 78,900 divided by 2,600. And we want this to be less than 60. And it is. It's 30 seconds. So yes, it will. 12. The diagram shows two black holes, A and B, orbiting each other. Assuming the center of mass C of the system is the center of the circular orbit for each black hole as shown in the diagram. Okay. Black hole A is an orbit of radius that, and black hole is an orbit of radius that. Both orbit with the same period, so the total distance between them is that. So I guess we're talking about if A is over here and then we're looking for this distance. Yeah, they haven't really thought that one through very well. Okay, so we're looking for the force, so F equals gmm over r squared. 6.67 times 10 to the minus 11. So the mass of the sun is that, and we have the mass of the black holes in terms of those. Okay, so here we go. So let's just do 36 times 29, and let's put in then times 1.99 times 10 to the 30. That does need to be squared though. Divide that by 6.5 times 10 to the 10 squared. Let's try putting this all in. And that gives us 6.5 times 10 to the 31 newtons. By considering the orbit of one black hole about C, determine the orbit of the period. Okay, so we're going to assume that this force is responsible for the circular motion. So we can say F equals mv squared over r, or m omega squared r. And omega is 2 pi f, or 2 pi over t. So let's say 4 pi squared r over t squared. So that's my omega squared in there. We're looking for the time period. So let's just swap that around with the force. So t squared equals 4 pi squared r by f. So that means that t is the square root of all that. So that's 4 pi squared times, now let's pick black hole A, shall we? So that's 36 times 1.99 times 10 to the 30 times the radius. Now this is the radius of the actual orbit here to the center, and we're told that for A that's 2.9 times 10 to the 10 divided by the 4, 6.5 times 10 to the 31. Let's cancel out some powers of 10, why not? Let's take away that, let's take away that. So 30, 31, so this is just 65. And that gives us a time period of 1, 2, 3, 4, 5, 6. That's 1.1 times 10 to the 6 seconds. Question 13. Distance to astronomical objects relatively close to the sun is determined using trigonometric parallax. For objects beyond a certain distance, standard candles are used. State what is meant by a standard candle. Well, standard candle is an object of known luminosity. That's the definition. Explain why trigonometric parallax is not used beyond a certain distance. Well, once you get beyond a certain distance, the angle there becomes too small. 2 marks. Well, you can use these angles, I guess. The problem is with that, as with most things where you have very small measurements, uncertainty becomes too great. C. Describe how distances too large for the use of standard candles can be determined. Redshift. Change in wavelength of known emission spectrum lines are used to determine speed, relative speed. And what do we do with that speed? Distance is determined using V equals Hubble constant times the distance. Easy. 14. Nuclear fission involves small nuclei joining to make larger nuclei. Nuclear fission involves large nuclei splitting to become smaller nuclei. Both of these processes release energy. The graph shows how the binding energy per nucleon varies with nucleon number for a range of isotopes. Use a binding energy per nucleon curve to explain how fusion and fission both release energy. So, when small nuclei fuse, binding energy per nucleon, it increases. Because we're going from, say, here to here. Therefore, energy is released. When large nuclei fission, binding energy per nucleon also increases, therefore energy released. And we may as well say fuse, nucleon number increases, and here nucleon number decreases. B. Explain the conditions required to bring about and maintain nuclear fusion. So, nuclei need to be at very high temperature, so they have very fast velocity / high energy. In order to overcome electrostatic repulsion of the nuclei and bring them to within 5 femtometers, i.e. range of strong nuclear force. In order to be maintained, enough energy must be released to cause subsequent fusions. We could also say that they need to be at a very high density. Question 15. Diagram shows apparatus used to investigate polarizing filters. Yeah. The intensity of light measured with no filters present is I0. So not surprised that even when the filters are parallel to each other, we only get half the intensity because half the light is being blocked. Okay, explain the effect of the filters on the intensity of light and why the intensity varies as shown. So the first filter, intensity of light to I0/2, by absorbing waves that oscillate perpendicularly to the direction of the filter. Now, if you really want to go into it, lots of people still adhere to the picket fence model, and so if your lines are like that, then waves that are oscillating parallel to those lines will be let through. That's not technically true. It is actually the opposite way round. In reality, what's going on is that if your lines are like this, waves oscillating like this can be absorbed by those lines. Waves that are oscillating perpendicularly, they can't excite the electrons inside the dark lines of the filter, so these actually get transmitted through. But that is overcomplicating it. It is true, but we're going to leave that for now. We're just going to say waves that oscillate perpendicularly to the direction of the filter. That's okay. So what's going on at 0 degrees then? At 0 degrees, filter 2 transmits, so lets through, all waves that were not absorbed by filter 1. Oh, I can't write today. As filter 2 rotated, bigger, now this is the word that they like you to use, bigger component. So make sure you use that word when it comes to polarization. Bigger component of light transmitted by filter 1 is absorbed until at 90 degrees when all components of light are absorbed. Therefore, intensity reduces to 0. So you know how it works. With these questions to do with polarization, it's all about just saying the right words. 16. Student is investigating a Cartesian diver. The diver is made from a plastic pipette. When placed in a plastic bottle full of water, the diver rises to the top and touches the lid. Show that the downwards force of the lid on the diver is about 0.02 newtons. Okay, so what is going on here at the lid? Well, here's our pipette, let's say, and we have the weight pulling down, yes, but we also have upthrust pushing upwards. They're not balanced by themselves. We also have the force of the lid pushing downwards, so we have 3 forces involved. So because we know that these forces are balanced, we can therefore say that the upthrust is equal to the force from the lid plus the weight of the diver pulling down as well. So therefore the force is equal to the upthrust minus the weight of the diver. Okay, and how do we find upthrust? Well, that's going to be the weight of water displaced. So let's find the mass of the water that has been displaced. That's the density times the volume. So that's going to be volume of the diver, 8 times 10 to the minus 6 times, well, just 10 to the 3. So ultimately that just ends up being 8 times 10 to the minus 3 kilograms. Therefore, finally, the force is going to be 8 times 10 to the minus 3 minus, I'm just going to factorize the whole thing here, 0.0059, and then we're going to times by g. So I can see that that's just going to be 8 take away 5.9, so that's 2.1 times 10 to the minus 3 times 9.8, and yes, I can see that's going to be pretty much 0.021 newtons. Not the easiest question in the world, that one. This is the tricky bit, realizing that all of those forces have to be in equilibrium first. Question B. When the pressure is increased by squeezing the bottle, water is forced into the diver, increasing its weight. The diver sinks, then remains at rest in the position shown. Volume of air in the empty pipette was 8 times 10 to the minus 6. So the volume now occupied by the air is about 6 times 10 to the minus 6. So not a terribly easy question again, but we can see that if it remains at rest in the middle, we can say that the upthrust is equal to the weight of the diver. Once again, this is equal to the volume of the diver times the density of the water that it's displacing times g is equal to the weight. They cancel, therefore the volume is going to be the mass of the diver divided by the density of water. So we have the mass from earlier, the mass hasn't changed, divided by 1000, that's the density of water, so that gives us 5.9 times 10 to the minus 6 meters cubed. C. Pressure of air in the empty pipette was 1.01 times 10 to the 5 pascals. Calculate the pressure of the air in part B. So we're talking PV equals nRT. What's staying the same? nR. We can assume that T is staying the same as well. So we can say P1V1 equals P2V2. We're looking for the second pressure, so it's going to be equal to that. So P2 is equal to 1.01, let's just keep it as that, it's just ratios, times the volume to begin with, and we saw that was 8 times 10 to the minus 6 divided by 5.9 times 10 to the minus 6, don't care about the powers of 10, so that's 8 divided by 5.9 times 1.01, and that gives us 1.4, but that has to be times 10 to the 5, just like our original value, 1.4 times 10 to the 5 pascals. 17. A coulometer or coulometer is used to measure charge. In a laboratory demo of the photoelectric effect, a sheet of zinc was placed on top of a coulometer and the zinc was given a negative charge. Following observations were made. Under normal lighting conditions, the charge remained constant. When illuminated with ultraviolet light, the magnitude of the charge on the zinc decreased as time passed. When a larger sheet of zinc was used, the charge on the zinc decreased more rapidly. In each case, the initial charge on the zinc was the same. Explain these observations. So under normal lighting conditions, the charge remained constant. So that means frequency of normal light was less than the threshold frequency. Therefore, photons did not have enough energy to liberate electrons from the surface. And we can say less than the work function. Second situation, when the zinc was illuminated with UV light, the magnitude of the charge of the zinc decreased as time passed. So if charge decreased, initial charge must have been negative, as UV photons had enough energy to liberate electrons from the surface. Final bit, when a larger sheet of zinc used, the charge on the zinc decreased more rapidly. Larger surface area means that more electrons were liberated per unit time, therefore charge decreased more quickly. B. For one sheet of zinc, the charge at different times was measured. Following graph was obtained. Students suggest that this is an exponential decay curve. Suggest how this suggestion could be tested. All we would have to do is check to see whether the time it takes to halve is the same in each case. Looks like it is. Calculate time taken for charge to half and compare at different initial charges. If times are equal, decay is exponential. 18. Light entering a normal eye is refracted by both the cornea and the lens before a focused image is formed on the retina. It is suggested that the cornea provides 80% of the focusing power of the eye. Determine whether this is correct. We're given the focal length of the cornea and focal length of the lens for a near object. So the power of a lens is equal to the reciprocal of the focal length. The total power is equal to power of one plus the power of the other. So let's find out what these powers are first. So power of the cornea. So that is 45. Don't forget that these need to be in meters. And then for the lens, 1 over 0.0527. That gives us 19. 45 plus 19 gives us an overall power of 64. Diopters, that's the unit for that. Therefore the percentage, well, we just want to know the bit, the cornea divided by the 64 times 100, it gives us 70%, not 80%. So it's a little bit less. B, light from a point object forms a focused image on the retina. The cornea and the lens may be treated at a single length, so focal length 1.6 centimeters, that is 2.4 centimeters from the retina. Calculate the distance from the point object to this single lens when a focused image is formed on the retina. So 1 over the focal length is equal to 1 over object distance plus 1 over the image distance. And we're looking for u, so let's just say 1 over u equals 1 over f minus 1 over v. 1 over 1.6 minus 1 over 2.4, 5 over 24. Therefore, flipping it on its head, u is equal to 24 over 5, 4.8 centimeters. A ray of light strikes the front of the cornea at an angle to the normal in air of 15 degrees. So that's our theta 1. Calculate the angle of the ray to the normal in the cornea. So we're looking for theta 2. Speed of light there, speed of light is that. So I always like to start with Snell's law, n1 sine theta 1 equals n2 sine theta 2. And we know that n1 is just 1 because it's the air. n2, well, how does that relate to speed? Well, that is the speed of light in a vacuum divided by the speed of light in the object. It has to be that way around because it has to be bigger than 1. So therefore, sine theta 2 is equal to v sine theta 1 by c. So that is 2.18 divided by 3. We don't need the times 10 to the 8, it's just a ratio. Times sine 15, and then inverse sine that. And we have 10.8, and let's round that to 11 degrees. C. People swimming underwater often wear goggles. Goggles enable them to see objects underwater clearly, whereas without goggles, objects appear blurred. Explain why wearing goggles has this effect. So we're talking about going from water to the cornea. We don't want that. We want it to go from air that's trapped in the goggles to the cornea. So the refractive index of water is 1.3. Refractive index of the cornea, we said, was 3 divided by 2.18, gives us 1.38. Light from water to the cornea, similar refractive indices, therefore less refraction will occur. Air to the cornea. And if less refraction occurs when we have light coming from the water into cornea, this results in power of lens reduced. And that's why things look blurry. 19. School science department keeps a sample of potassium chloride to use as a test source for GM tubes. Potassium contains 0.012% of the unstable isotope potassium-40. Potassium-40 undergoes beta minus decay, producing a stable isotope of calcium. Complete the nuclear equation for this decay. Easy peasy, we know that the mass of a beta or electron is basically 0, and the atomic number is -1. It has a charge of -1. Therefore, mass stays the same, calcium-40, but the atomic number goes up by 1. Teacher makes some measurements using the potassium chloride test source to determine whether a GM tube is sufficiently efficient at detecting beta radiation. Potassium chloride sample has a mass of 300 milligrams. So that the number of nuclei of potassium-40 in the sample is about 3 times 10 to the 17. Number of potassium nuclei in 1 gram of potassium chloride is that. Oh, that's nice. They've given us the number of nuclei. Okay, so 1 gram equals that. So therefore, 0.3 grams, which is that, is equal to, well, 8.1 times 0.3, and that gives us 2.4 times 10 to the 21 nuclei. Then, how much of that is potassium-40? Well, it's only this 0.012%. So we need to take this 2.4 times 10 to the 21 and times that by 0.0 and then 0.0012, and we end up with 2.88, let's call that 2.9, times 10 to the 17. Show that the activity of the sample is about 5 becquerel. Half-life potassium is 1.25 times 10 to the 9 years. Okay, so we're talking becquerel, so that's seconds to the -1. So we first of all need to turn that into years. So T half is 1.25 times 10 to the 9 times 365 times 24 times 3,600 days, hours, seconds. And that is 3.94 times 10 to the 16 seconds. But we're not looking for the half-life, we're looking for the activity. We know that activity equal to lambda n, where lambda is the decay constant. We know that it's linked to the half-life by log 2. Decay constant is log 2 over the half-life. Again, that's times by n. So let's put this all in. Log 2 times the number of nuclei that we had from earlier is 2.9 times 10 to the 17. Divide that by the half-life, 3.94 times 10 to the 16. Lo and behold, that gives us 5.1 becquerel. With no sample in front of the GM tube, a count rate of 15 counts per minute is recorded. When the potassium chloride test sample is placed next to the Geiger-Müller tube, 176 counts are recorded in a period of 10 minutes. Okay, so that's 17.6 per minute. A detector is considered efficient if it detects at least 7.5% of beta emissions from the source. Determine whether this GM tube can be considered efficient. So the measured count is 2.6 per minute, but the source emits 5.1 times 60, so that's 306 per minute. So we can already see that's going to be nowhere near to 7.5%. Let's just check. 2.6 divided by 306 times 100, and that only gives us 0.8%. Not efficient at all. Explain a possible reason why only a low proportion of the decays are detected. Well, first things first is that the detector is a fairly small area, whereas the source is emitting in all directions. But we also have this casing as well, and you also have the sample as well. So absorption may occur before beta particles reach detector. C. The science department also has a sample of strontium-90. This undergoes beta decay with a half-life of 29 years, as opposed to, what did we have earlier? We had 1.25 times 10 to the 9 years. Just a tiny bit longer. State why the half-life of potassium-40 makes the potassium chloride a more suitable material than strontium-90 for the test. Well, a relatively short half-life means the activity of the source will change significantly over time. 20. In 2016, scientists at the Laser Interferometer Gravitational Wave Observatory, understandably shortened to LIGO, announced that gravitational waves had been detected. Signal they detected is shown on the graph. Gravitational waves travel at the speed of light. Determine the mean wavelength of the waves detected between 0.3 and 0.35 seconds on the graph. We're looking for the wavelength, so therefore wavelength is equal to speed divided by frequency, but we have the time period, so it's just going to be v times the time period, so there's 3 times 10 to the 8 times, well, let's say that's 0.05 divided by 2. There's 2 waves in there, so 3 times 10 to the 8 times 0.05 divided by 2, and that gives us 7.5 times 10 to the 6 meters. B. Gravitational waves alternately compress and stretch matter by a very small amount as they pass through. The LIGO detector has 2 arms at 90 degrees to each other, each 4 kilometers long. As a gravitational wave passes the detector, the arms change length. The detector continuously compares the lengths of the 2 arms. An article states that the maximum change in the 4 kilometer length of the arm is about 0.001 times the diameter of a proton. Determine whether this statement applies to the gravitational wave shown in the graph. Okay, so we're measuring the strain here in times 10 to the minus 21. So we're going from 0 to 1.2. So the strain is 1.2 times 10 to the minus 21. And we know that is equal to change in length by original length. We're trying to find the change in length. So therefore, It's going to be 1.2 times 10 to the minus 21 times 4 times 10 to the 3. So that gives us 4.8 times 10 to the minus 18 meters. What about this? Article says that it's 0.001 times 8.8 times 10 to the minus 16. So ultimately that's just going to be 8.8 times 10 to the minus 19. So we have these two numbers. They're quite a bit out, factor of 5.5 out. Part 2, in the LIGO detector, any change in the length of the arms is detecting using a laser beam and a photodetector. The laser beam is split into two at B, one beam travelling to the mirror, yada yada, and then they're recombined, so very similar to the Michelson-Morley interferometer. Photodetector measures the intensity of the incident light. The system is arranged so that when no gravitational waves are present, the beams have a path difference of half a wavelength at the photodetector. Explain how the photodetector detects very small changes in the length of one arm when the other arm stays the same length. So we can just say when one arm changes length, path difference of two beams also changes. When pi radians out of phase, destructive interference occurs, and a minimum is detected. We can say zero intensity. If path difference changes up to 1 lambda, constructive interference occurs, resulting in a maximum. Lastly, the system could be arranged so that when no gravitational waves are present, the beams have zero path difference at the photodetector. Explain whether using an initial path difference of half a wavelength is a more sensitive way of detecting changes in length than having an initial path difference of 0. Half a wavelength path difference is going to be better. If path diff is lambda, maximum detected, more difficult to detect the change in intensity. So I hope you found this helpful. Please leave a like, and if you want to go on to paper 3, click the card and I'll see you there.